Okay, section 7.4 is all about cardinality and countability. So we have two things in this section to talk about. The first is cardinality and its properties. So this is cardinality properties. Then we're going to discuss a little bit about countability. Countability of sets. So cardinality is a special property of sets that we look at. It's very similar to size. It does have some differences. So this is for all sets, A, B, and C. Our first property of cardinality is that A has the same cardinality, of B if and only if there is a bijection from A to B. So the reason for this is that cardinality, while similar to size, we could have infinite sets, and obviously then those have infinite size. So if we're going to use cardinality to describe sizes, we need a better way to determine if two things have cardinality than saying, do they have the same size? And the reason for that is this has kind of fallen out of vogue in mathematics in recent years, in the last decade or so, maybe more. But we used to always describe infinity as having different levels of infinity. But at the end of the day, infinite is still infinite. But there are some infinite things that are just bigger intrinsically. And we're going to talk about that when we talk about countability. But for example, we've talked about how in between every integer, there's an infinite number of fractions. Well, if there's an infinite number of fractions between every two integers, there's also an infinite number of integers. So we know that the integers are infinite and the real numbers are infinite, but there's definitely more real numbers than there is integers intrinsically. Now, literally, that's not the case. Literally, there's an infinite number of integers and an infinite number of real numbers. So cardinality ignores the size, quote unquote, and looks at, is there a one-to-one and onto, or is there an injective and surjective function that maps A to B? If there is, then they have the same cardinality. Now our second property of cardinality is the symmetric property. So the symmetric property says if cardinality of A is the same as B, then the cardinality of B, cardinality, is the same as A. Now if we combine this statement with statement 1 here, to have the same cardinality A as does B, that means that there's a bijection from A to B. And then to say that the cardinality of B is the same as A says that there's a bijection from B to A. Now we know, since we have a bijection, it's one-to-one, which means that it's invertible. So it makes sense that this should be the case. Since we have a bijection, we can invert that bijection from A to B to go from B to A. And we know from the last section that if you have a surjective function, its inverse is then also surjective. So not breaking any rules here. Next is the reflexive property. And this says that A has the same cardinality as A. Now you may think this is trivial, but this is basically saying that you can form the identity function or the identity bijection onto any set A. Our final property is the transitive property. And that is that if A has the same cardinality as B, B has the same cardinality as C, then A has the same cardinality as C. Cardinality as C. Now cardinality from our 4 properties here, you'll notice it just works the way that we would want it to if you think of it as size. So it makes sense on a base level. If A is the same size as B, then B is the same size as A. A has the same size as A. If A is the same size as B and B is the same size as C, then A is the same size as C. Again, though, we use these definitions because when we're dealing with infinite sets, size becomes a little weird. But also, you can think of cardinality as, can you form a bijection? Because that's our base property, is to have the same cardinality, you can form a bijection. So if I tell you there's a bijection between 2 sets, then you know that they have the same cardinality. And vice versa. If you want to know, does a bijection exist, and you know that they have the same cardinality, then yes. It also means that proving things have the same cardinality is the same as proving that there's a bijection, which comes down to proving that it's injective and surjective. So you have to have a mapping. So we're going to look at a couple examples, some proofs, and some countability stuff after this. All has to do with cardinality. So let's start with a little proof about cardinality. So we're going to let 2z represent the set of even integers. So that means we're just eliminating all the odds. And this proof is good to kind of illustrate why cardinality and size is not the same. Because we know 2z is half as many integers as the whole set z. And so we're going to prove that z and 2z have the same cardinality. So that means that we have to have a mapping from z to 2z or from 2z to z. And we have to show that that mapping is a bijection. So we are going to first consider the function h, no space there, h that maps z into 2z by h of n equals 2n for all n in Z. So when you're constructing functions like this, you really should start by showing that it's well defined, that you don't have an ambiguous function. Remember, that means that it satisfies the definition of function, our new set definition that we have. But since we've used this before, this 2n, it's the linear function 2n. We know that this is a function, so I'm not going to go through that. Just keep that in mind that you may need to show something's well defined in the homework. So what we need to show is that this h of n is both injective and surjective. So we are going to suppose h of n1 equals h of n2 for n1 and n2 in Z. Then that means that 2n1 equals 2n2, or n1 equals n2. Thus, h is injective. We took arbitrary elements in our domain, assumed that h of n1 is h of n2, and showed that the domain elements therefore need to be the same. Definition of injectivity. Next, we're going to let m be an element of 2z, be arbitrary. By definition, there exists an R in Z such that m equals 2R. So h of R then equals m. This is by definition of h. So h is surjective. And since we have an injective surjective function, we have, therefore, h that maps Z into 2Z is a bijection. And so Z and 2Z have the same cardinality. So they have the same cardinality, but again, we know that 2Z has much less, half as less elements as Z, but they are both still infinite. So you can construct a map, a one-to-one surjective map. So everything in Z maps onto everything in 2Z, even though we know there's half as many. But because they're infinite, it does weird things to our sizes, and more so to the countability. So countability is a really interesting problem, and in number theory, it's one of the most studied properties. So countability has a couple different definitions associated with it. So a set is called countably infinite. Countably infinite if and only if it has the same cardinality as z plus, the positive integers, because those are what we count with, otherwise known as the natural numbers. A set is then countable if it is finite or, need more space, so a set is countable if it is finite or countably infinite. Otherwise, it is uncountable. So the term countability comes from the fact that we count using the natural numbers, the positive integers, 1, 2, 3, 4. So if we can construct a bijection from those counting numbers to an infinite set, then we can say that that set is countable. We call it countably infinite to change the fact that it's not finite. We can't actually count up all the values because, as we've said in the past, if you try and do something that's infinite, you'll die before you ever finish it. So the first thing we want to do is show a very, very specific case. And we are going to show that the regular integers, that z, is countable. So this is something that a lot of people take for granted, but it is important. You have to have a bijection to z positive. So we have to show that z and z positive have the same cardinality. Z and z plus have the same cardinality. Which just means find a bijection between the two. Now, a lot of people's first ideas here are to jump to the absolute value of n. The problem with the absolute value of n is that the absolute value of -1 equals the absolute value of 1, and -1 does not equal 1. Which means that the absolute value of n is not injective. So while we do have a mapping from the integers to the positive integers, we do not have a bijection using the absolute value of n. So the function that gets used most often, h of n equals piecewise defined n over 2 if n is even, and negative n minus 1 over 2 if n is odd. And this is specifically taking the positive integers into the regular integers. So 1 is odd, so we have 1 minus 1 over 2, 1 minus 1 is 0, so that goes to 0. That's how we get the 0, because remember the positive integers doesn't contain 0. 2 is even, so 2 goes to 1. 3 is odd, so we have 3 minus 1 over 2, or 2 over 2, negative makes it -1. 4 is even, so it goes to 2. 5 is odd, so we get 4 over 2 and make that negative, so that gives us -2. 6 is even, goes to 3, and etc., etc. Now this was, when it happened, was a big deal in math. Finding this specific bijection that shows that, yes, this larger class of infinity is still countable. Now, again, we take that for granted because if you could count the positives, why can't you count the negatives? They're exactly the same thing. And you'd be right. You still have to prove that in mathematics. So we have that our integers, the full set, are countable or countably infinite. The next big set is to show that the rationals, specifically the positive rationals, Q plus, is countable. Well, now we're starting to get a little more difficult because now we have all the integers and we have also all of the ratios of integers. Now this one's a little bit harder to write out as a full function. So what I'm going to do is kind of write out the pattern that was used to prove that Q plus is countable. And the idea here is if the integers are countable and we just start looking at integers over integers, well, for every integer we pick, 1, 2, 3, we should be able to count all of the rationals then that get formed with that number in the numerator. But we know that fractions have equivalent fractions, especially rational numbers. So we need to not count those, because if we count all of those, then we have a lot more numbers. And the idea is you are countable when you can limit the number of elements you're actually looking at. So what we're saying here is we have 1 over 1, 1/2, 1/3, 1/4, 1/5, 1/6, dot, 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 dot. We make all of those rational numbers. Then we make all of the rational numbers that have 2 on top, 2 over 2, 2 over 3, 2 over 4, 2 over 5, 2 over 6, dot, dot, dot. We have all the ones with 3, 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, 3 over 6, dot, 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 dot. And that continues on down that way. And then we're going to keep writing because there's a bunch. But notice that we repeat 1 over 1, 2 over 2, 3 over 3, all the same thing. 1/2, 2 over 4, 3 over 6, all the same thing. 1/3, 2 over 6, and down here would be 3 over 18, all the same thing. So we need a way that doesn't actually count all of those repeats. But each of those repeats, some of them are going to be rationals. Or, I'm sorry, not rationals, they're all rationals. They're going to be integers. So we start with 1, and we move to 1/2. Then from 1/2 we take the reciprocal, and we go to 2 over 1. From 2 over 1 we go to 3 over 1. From 3 over 1 now we go to the reciprocal, we skip this, and we go straight to 1/3, skipping over this repeat because we've already counted it. And then, now that we're at a new 1/3, goes to 1/4, 1/4 goes to 2/3, 2/3 reciprocal goes to 3/2, 3/2 would go down to 4 over 1, 4 over 1 would then jump down to 5 over 1, and then it'd repeat. And it would ignore this, and go straight back to 1/5 from 5. So you can see the pattern in these diagonals. Then from 1/5 it'd go to 1/6, 1/6 to 2/5, 2/5 to 3/4, 3/4 to the next one, and so on. And then you would go all the way down and it would come back around, and you would do this ad infinitum. But it allows us to map every single real number or every single integer to a rational number. 1 gets mapped to 1/2, 2 gets mapped to 3, 3 gets mapped to 1/3, 4 gets mapped back to 1/5, so on and so forth. And this would continue forever. But every single one of our integers gets mapped to a specific positive rational. Now this mapping doesn't work for negative rationals, but this is how it would work. So that's why our positive rationals are countable. And again, you start counting, quote unquote, at 1, and it follows this pattern over and over again, and you're only ever skipping equivalent fractions. So 2/6 is an equivalent fraction to 1/3, so that gets skipped. 3/5 is not. 3/5 would not get skipped. So when you come back around, it would get to here and then skip 2/6. And this is a relatively simple construction here, but notice that this would be 4/2 here if this was 4/1. This would get skipped. And there's a lot more that would not get skipped. But as you go out in this pattern, we really start to get a muddled mix of sometimes we skip, right? These two diagonals we skipped everything. But in this diagonal, for example, we're going to skip 2/6, we're not going to skip 3/5. And then the next one would be 4/4, we're going to skip that, but we're not going to skip 4/3. And so you start to see that pattern develop. Sometimes you skip everything, sometimes you skip every other thing, sometimes you skip every 2 things. And it just gets more complicated as you extend this out. But this is not something that we can write out in a neat, clean expression like we could with this, for example. So we have this mapping. So now we want to talk about some things that we can't count, because there's no bijection that maps properly. So the first is the set of real numbers from 0 to 1 is uncountable. So if you think of this as there's no function, bijective function, that maps from integers to the set of real numbers from 0 to 1, just think about all the fractions between 0 and 1. There's an infinite number that start with 1. There's an infinite number that start with 2. There's an infinite number that start with 3. And by start, I mean have it on the numerator. Right? You have 1/2, 1/3, 1/7, all of these, so on and so forth. You have 2/3, 2/5, 2/7, etc., etc. There's just too many, and how do you map integers properly? We can't use the same trick. People tried, but you can't use the same trick because you have 2/3, but you also have 2/3 millionths. And then that continues on and on. So the problem with the previous mapping is that it skipped equivalent fractions. Well, we have way more equivalent fractions than we did in the rationals, because we also have all the irrationals. So not only do we have these nice things, we also have things like the square root of 1.5. We have the square root of 1.9. Things like that. So how do you map integers to these irrationals? You can't. So the set of real numbers from 0 to 1 is uncountable. Now the next two theorems are how we extend countability to other sets that we know. So the next theorem is any subset of a countable set is countable. Which makes sense. We took all the even integers, which is certainly a subset of the regular integers. and show that that's countable. Or at least that has the same cardinality, and since the integers is countable, that means that the even integers are also countable. So that's one big thing. If you can show that the big set is countable, like integers or rationals, then if you take subsets of those, you still have countable sets. And then any set with an uncountable subset is uncountable. So if we combine this with our first theorem, the set of real numbers from 0 to 1 is uncountable. The real numbers subset has a subset that is uncountable, so the real numbers are uncountable. So that's the big takeaway, is that R is uncountable. And from here, since R is a subset of the complex numbers, C is uncountable. So there's a fun little train of subsets that we can construct here to try and talk about this. So let's start with the counting numbers, Z plus. These are a subset of the regular integers. The integers are a subset of the rationals. The rationals are a subset of the reals. And the reals are a subset of the complex numbers. So this is our counting numbers, our positive integers. We know that this is countably infinite. And our rationals are also countably infinite. Now I said that we couldn't use the same bijection a little bit ago that we used here to show that Q is countable, but as it turns out, once we have Q plus, the positive rationals, countable, then you can form a bijection from Q plus into Q. And you can look that up. There's a couple of them that people have found throughout the years, again, because countability is one of the most studied concepts in number theory. But it turns out the rationals are countable, which again makes sense. If we can count all the positive integers, we can count all the positive rationals. And if we can count all the negative integers, which is what C being countably infinite tells us, well then why can't we count all the negative rationals? Turns out, yes we can. R, though, is uncountable. And since R is a subset of C, that means now C finally has a subset that's uncountable. So by our theorem here, is also uncountable. So we kind of have these hierarchies of infinity. And like I said, this is, you don't see this taught very much anymore, and I'm not saying that this is true. I never thought that it made sense myself, but the degrees, so to speak, of infinity, all of these sets are infinite. But we know that the complex numbers are the largest of the infinite set. And so to get around that, that's why we use cardinality. When you're dealing with finite numbers, or finite sets, so when sets are finite, cardinality equals size. They're the same thing. But when you're dealing with infinite sets, cardinality and size are different because infinite, 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 they all have the same size, quote unquote, but their cardinalities are different from here to here. And that's the issues. This has the same cardinality as this. This has the same cardinality of this. But these two things do not have the same cardinality. And so if you're curious as to why they don't, you can look up something called Dedekind cuts. And this relates the rationals and reals. I think this is Dedekind with an E maybe. I'm trying to remember off the top of my head. And the Dedekind cuts are, I'm blanking a little bit, it's either how we get the rationals from the reals or how we get the reals from the rationals. But it's not a bijection, and there's no way to make it a bijection. But it is an interesting topic if you want to look it up. But it's how we know that the cardinality of Q is not the same as the cardinality of R. And if these two aren't the same, well, since this has the same cardinality as this, and these aren't the same anymore, that means this and Z don't have the same cardinality, and Z plus and R certainly don't have the same cardinality. That's the idea here, is we can be countable, we can be countably infinite, or we can be uncountable. And you can think of cardinality as kind of the glue between that. And I personally like to think of cardinality as, can you form a bijection? Is there a one-to-one and onto function that maps one to the other? Okay. So that's the end of 7.4, and with it goes chapter 7.